Everybody want it?
We do hope so. Okay, good morning, everybody, or whatever time it is, wherever you are. Welcome to this webinar from the Institution of Mechanical Engineers. Just a couple of quick housekeeping notes before we start properly. We will be recording the event, and we will make a record of the event available through the Process Industries Division YouTube playlist at some point later. We've generally disabled attendee media in order to try and make sure presentations work smoothly. There will be questions, I'm sure, when the speakers start to speak. There's two options for that. One is through the chat, and there's probably better, however, is through the Q&A function. So somewhere at the top of your screen in Teams, you should see a little Q&A bubble. It's like two speech bubbles. The reason perhaps for using the Q&A is that it's relatively easy for others who have a similar or same question to sort of upvote it, and we will be able to see the questions that are most interesting to the most people. A little bit later, we're going to potentially make available slides, but in general terms, I would ask you to rely on the video. So, about this session, about this webinar, this is the final event in a series of webinars that we'd called Steel with Pride, which isn't terribly snappy, but does seem to describe what we've been talking about. We hope today to provide a little bit more information in terms of particular subjects, and those subjects are around human factors, human reliability, and ethics, to also summarize the sessions that we've had so far. So the agenda for today, this morning and through into the early afternoon, I'm going to look back first over the Steel with Pride series of webinars that we've been running since 2021. We'll then have a session from people with expertise in human reliability and safety critical settings, so a little bit around some techniques to reduce human error in high significance activities and some practical applications. We then need your input, because we have some case studies to look at and some discussions to have around the ethics of decisions versus safety and environmental protection, but with respect to how engineers make decisions. We're going to look at frameworks for raising concerns and the need to apply lessons. Discussion of a suitable record of the series is something that we will need to ask your input on, and then at the end of that, I'll try to reflect. Okay, so moving on then to a summary of the series. We started in 2021 and we've been running to date. My name's Richard Roth. I'm Group Process Safety Director for Costain as a day job, but I've been involved with this series throughout. My background is roughly 20 years in the chemical industry, 5 years in steelmaking, and now 10 years in the construction world. So that's the experience I bring, but we often have speakers in the audience who have different, more expertise than us. So please do share if you've got comments through the Q&A, as I say. Okay, the series back in 2021 was launched with a retrospective. Took an opportunity to look back over 50 years of catastrophic incidents. I was prompted to take that 50-year cycle because 25 years ago I'd been sitting in the audience of a session that looked back on 25 years, and I thought, firstly, I've been around for too long, but secondly, well, let's look back and see what it is that we should have learned over the years. I looked at serious incidents, which do remain far too common, unfortunately. I looked at 10 incidents across the decades, from transport systems, structural collapses, water industry problems, food production issues, oil drilling, nuclear power, and material storage. And I didn't always choose the most newsworthy of incidents in each of those, but actually the incidents were definitely newsworthy, at the very least nationally, if not globally, in terms of the ones I chose. We noted that the lessons from those incidents across those 50 years included the need to focus on safety critical communications and safety critical information. We needed to focus on the management of non-standard or degraded ways of working, so temporary change, one might say. We noted the need for clarity of design intent, because if we build something that wasn't what the designer had in mind, it may react differently. We needed, with that in mind, to think about management of change. If we either operate or construct or use or demolish a facility in a different way than that which was intended by the designers, we can end up in trouble. But we also noted that things that are difficult to construct will tend to lead to uncontrolled change. We also noted that a key lesson from such incidents across the years is that design studies need the right experience, right diversity of experience in the room to be useful. A design study that doesn't have operations experience, for example, or construction experience or designer input can end up with either narrow or incorrect conclusions. Other features worth noting: if we reduce the consequence of any given catastrophic incident, we can make sure that the risk is reduced. And by reducing consequence, when we're talking about safety of people, if the people aren't near the item that explodes, collapses, releases something noxious, then they can't be injured. So actually thinking about consequence and making sure that people are separated from potentially hazardous situations is a useful way to reduce risk. Other features, you'll see in the photographs that I've got, just a short list of photographs there. The one at the bottom is nuclear power facility where they were trying something out. They were doing experiments, and so temporary changes should also be seen as changes. We need to be clear that temporary changes need to be authorized and managed in much the same way. We also note that organizational culture can prevent challenge. So if a culture is such that people don't speak up, then people won't speak up, and that's one of the reasons we've included a session today around engineering ethics. However, organizational culture can have the opposite effect. The right culture can promote challenge, can promote the raising of issues and the solutions that follow. We also noted from the incidents we looked at that some mundane tasks can become safety critical barriers, and recognizing when things that are mundane are in fact safety or environment critical is really important, because mundane things are easy to forget, drop, cancel or whatever. And so it is important to think about actually what are the barriers to a catastrophic incident or a process incident, and make sure that we know that those are still happening, which I'll come back to in a moment. One of the incidents we looked at in food manufacturing was a dust explosion, and all I would say is do remember that whilst dust needs 5 things to explode, when it does, it can be just as destructive as flammable gases and vapors. So just remember dust. And a final one, I guess you're all here at a process safety webinar, so you'll perhaps understand what we mean by process safety, but organizations can find it easy to focus on occupational safety, the things that are causing minor injuries immediately today, almost every day. So organizations need to be careful not to have their time and their management time sapped away from process safety. I guess a final point, there is a difference between learning lessons and applying lessons. So here we are sharing some, but at the end of today, I guess you should all reflect on, well, how can I do something different about what I've heard today so that I can apply those lessons? Okay, so that was the series launch. The subjects we covered, essentially it's the quality cycle as applied to process safety management. And the quality cycle is often summarized here as plan, do, check, act, but there's a little bit more detail required. So we do need leadership in order to make the circle go round. We need to make sure that our organization has clear procedures and guidance and training of that. So people do need to understand what it says in the procedures and guidance, and they can be helped to do so. It is important that we assess compliance. One of the ways we can find out how we're doing is when incidents occur, but they ought to be rare. And if they are rare, therefore, there isn't much data. So actually, organizations need to go check, need to have assurance audit in place. Now, when an audit is done, for me, there's an expectation that we'll find something, and that shouldn't be seen as a bad thing. That should be seen as data for management to take action on. So as I just mentioned, the other way to find out how things are going is when unexpected events occur. Now, we don't have to wait for a disaster before we investigate. Most organizations that I'm familiar with have approaches to investigating potential incidents, sometimes called near misses, close calls and so on. But in essence, if we recognize the potential of an incident could have been much worse, then we ought to be applying the same sort of thinking as though it had happened. All of that provides data. It is important, therefore, for organizations to analyze their data and information, and for management teams to engage with that data. This is not some esoteric process done by specialists. It is important for line managers to see the data, potentially to ask their specialists, what is this telling me? But not just to see a single traffic light. It is important that managers interact with process safety data. And then, of course, we may choose to change. We may choose to change because we want to act on some data, or we may choose to change because we've got a great idea, or we may choose to change because we've seen a great idea from somewhere else in another sector or another organization that we'd like to apply. All of that is great news because that is a continuous improvement cycle, but For your change, go back to the top of the list. Are we leading it? Is it clear what the change is? Does everyone understand it? Are we assessing whether or not it actually has happened as a change? And separately, whether it had the effect we wanted it to have, particularly if it was intended as an improvement. So change can potentially throw a spanner in the works of this nice, simple, circular plan, do, check, act. So from leadership, we looked at the Herald of Free Enterprise incident, and we extracted from it some lessons that are specifically around leadership. Clarify roles and give authority to act. It is important that that it's clear who makes the decisions, who's their deputy, who is in control of which part of any given activity. But alongside that, we need to maintain an open culture. And although the sentence is incomplete here, the open culture is for listening to messages from our organizations. It is important that leaders avoid focusing on the absence of loss, by which I mean, if we focus purely on incidents, as I mentioned a moment ago, we won't get much data, but also we might be surprised, and not in a good way, when a serious loss occurs. So if we move from measuring the absence of loss to the presence of barriers, then we're in a much better place. And audit's one of the tools we can do that. The other feature that was associated with the session we did on leadership is around organizational change. So not just physical changes. It may be that once we change organization, new tasks have become critical, and or tasks that were critical may not be resourced in the same way. So it is important to think about what our people do and what the roles within our organization are responsible for. Of course, humans are always fallible. As you can see from my lack of an ending to the second sentence in this slide. But my point is that if humans are fallible, actually, we can probably assess how fallible and what circumstances. And our second session today will come back to something like that. And of course, when there are competing needs, we should be clear that our leaders need to stress a safety first type of message, and by deeds and not just words. So if I am saying safety first as a leader in your organization, but it isn't the thing I pay most attention to, then you'll probably look at my deeds and not my words, and draw your own conclusions from that. Okay, so we need to define critical tasks, preferably what must go right, the barriers, what has to be in place within your procedures. And if we focus on what has to go right, we can then ask, do we have enough suitably qualified and experienced people to deliver that? And do we know that they know what has to go right? Certain organizations have to manage a lot of change in organization and organizational content and makeup quite routinely. And most of their time then is spent reiterating, here's how we do things around here. If you work in a relatively consistent organization, you may not have to do that reiteration so much, but auditing can find out whether we're sliding away from where we want to be. Okay, so if it's not already clear, I think audit's really important. So assurance audit's vital. It's a vital tool in performance discovery, and actually all aspects of a quality cycle. This particular cycle is based on the ISO models that we've got on the image today. We can check all of those. We can check leadership, planning, support, operations, improvement. So we're trying to ask ourselves the question, do we understand what could go wrong? Do we know what systems we have in place to prevent that happening? And do we have information to assure us that that's happening? So you may recognize those questions. Those questions were put to journalists on the steps of the court after the investigation and the court case associated with the explosion at Bunsfield. And it was the HSE inspector who asked those questions. But those are three really good questions to ask when any organisation. However, as far as audit is concerned, it gives us some of the answer, if not all of the answer, to the third question. Do we have information to assure us that they're working effectively? So when we talk about learning from untoward events, the session we had was based on a rail incident that occurred in Carmarthen, Scotland, not that long ago, but we looked at how the Rail Accident Investigation Branch had created its report, how it had gone about its investigation. So thorough investigations need trained people and they need time. And in fact, perhaps more importantly than that, they also need sponsorship from line management. The investigation for any untoward incident in the organisation that you work in, if the line managers want it to happen, then we're in a good place because they will then own the findings and hopefully recognise those findings and potentially be able to make improvements. As some of you will well know, the transport accident investigations in the UK for air, rail and marine are done by not-for-blame independent organisations, and that isn't true necessarily for the generality of health and safety investigations, and it's also not necessarily true in intra-organisational investigations, but we can create some level of disinterest and independence in an investigation team. But yeah, I would say it is important to make sure that your investigators have some help and therefore some training in order to do a professional job of investigation. If we get investigation done well when it's required, we can identify deep issues that underlie the problems. We can make well-targeted recommendations at those deep issues, and we can then at least set up lessons which, if recommendations are responded to by the right actions, will apply those lessons. And anybody who knows me will know that it's kind of important, the difference between writing it down and then doing it differently next time. And that's something that management teams need to understand and recognise. When looking at data, we focused on a number of incidents. We focused on a number of aspects of data. So there's my three questions again. What can go wrong? What must go right? How will we know? But it is important that leaders see, discuss, and actually engage with information. And that information needs to focus on the barriers. So what are we doing to make sure that incidents don't occur? It can give advance warning of degradation and barriers. Potentially, if we're measuring a leading indicator about the state of a barrier, if we know that it's beginning to degrade, we can fix it before there's actually any kind of loss or harm. The other feature that looking at data can do, especially if you look at a suite of indicators, is allow for weak signals to be identified. Weak signals in those data might mean a particular part of the organization suffering a number of dips at once, or a particular subject suffering a number of dips across the whole organization. And these things can allow a strong response before even minor incidents occur. But try to pick leading indicators, try to pick indicators that tell you something about barrier performance, which will give you and your management teams opportunity and time to respond. There is an important point about data can be difficult to engage with, particularly for people who are short of time. So it may well be that we need specialists to interpret that data, but it is the organization's data, not the specialist data. And it's kind of important that the data become information and that the information is then used to make good decisions by management teams. So when we looked at change, we've focused on a particular incident from the UK at Flixborough, but we wanted to identify that change needs to be thought about in three streams: physical changes, changes to the process being undertaken, that might be a manufacturing process or a chemical process, but also organizational changes. And we tried through the case study for that event to focus people on the need to recognize when change is happening, because it isn't straightforward to do that. Sometimes changes are made within a range and that's acceptable, but getting outside that range might not be so clear to everybody. So recognizing change, defining or designing the change, as in being very clear about what it is that's about to change, and not only what it is that's about to change if it's physical, but how it will change and over what period and so on. Need to make sure that the right people authorize changes and that the right people have had their say. A moment ago, I talked about hazard studies needing to have diverse experience in the room, and authorization of change is no different in the sense that assessing whether it is a good idea, as in, is it good business, will it likely have the desired effect, and can we enact change, are things that we need a few different brains around the table to assess. It's important to record what has happened, not only just for the sake of updating drawings, but a few years, months down the line, we might not quite remember why we made that change. It is important to be able to get back to the records and to be able to see what is new, what's different, and for that to look like what it looks like out in the field. Plenty of you will have experience of drawing systems not quite keeping up with reality, and so not only is the record updating the drawings, but it's perhaps updating the reasoning behind the thinking as well. And the final piece is, of course, if you've changed something, don't expect everybody to just understand that by osmosis. You have to communicate what it is that's changed, why it's changed, and therefore what they might need to do differently about that. Okay, well, one of the other presenters today, who you'll speak to in a moment, focused me back towards Trevor Kletz, and Trevor Kletz is a process safety guru, certainly from the chemical industry, and often people choose quotes from some of the things that Trevor has said, reputed to say, often said. One of the ones I particularly like is one that I do use with managers in the organizations I work with. So after an accident, managers will often say, I did not know this was happening. If I had known, I would have stopped it. And Trevor then usually says, it's bad management. The manager's job to know what's going on. And he says it with total amazement. And actually, I think he's right. And I agree with this one. And it's particularly important for you if you are advising or working with managers. If managers say, well, I don't know what's going on, then there may be something about prioritizing their time that we might be able to help with. I think it's quite important that we don't set our managers and leaders up to have so much on that they can't possibly know what's happening. And when I talk about organizational change, that's one of the areas to think about. Other quotes that are worth thinking about that I haven't got on the screen, which relate to my point about applying lessons, is when an incident had occurred, Trevor would say, don't bother doing an investigation. I've got one in my file that's exactly the same as what you're about to find out. And hence he ended up writing books called Still Going Wrong. So the concern there is we're able to write down the lesson, but we may not be applying it. Okay, So we, over the series, have recognised that catastrophic incident risks, process safety risks need distinct focus management, and if you understand that quality cycle and you are clear that all of these items are being applied in the organisation you work in, then you're probably in better control of your risk than otherwise might be the case. So that's my roundup of the events so far. I'm going to stop sharing. I'm going to ask the next two presenters to just come onto screen, and we'll do a little bit of a handover, and we'll get on with the next session. I should say before I do hand over to Richard and Stuart, that we'll take a break after this next session, but there is a chance for a couple of questions at the end of this session. So, as I say, use the Q&A. I'll monitor that, and we will get on from there. But the next session, firstly, I'll let Richard and Stuart introduce themselves, and then get into the next session. And I will see you all shortly.
I'll start off with me. I'm Richard Hellebrand. I've been IMechE for donkey's years, but I've also been a member of the Energy Institute and fellow of the Institute almost as long. So I sort of sit in both camps, but I've got some experience with safety critical tasks at COMA and Seveso sites, but I'm not an expert. But Stuart is, I hope. So Stuart, I think if you introduce yourself, and Stuart's going to run most of this session, and I'm just going to chip in at the end with an example.
Excellent, thank you, Richard. Yes, morning everyone. So my name's Stuart King. I'm technical manager at the Energy Institute, and I look after our human factors work programme as well as our power systems work programme, and that includes our activities around incident investigation as well, and various other activities. So let me just share my slides. So, well, I won't exactly call myself an expert. Let me just double check whether this is that sharing the right slide?
Yep,
it's clear, Stuart.
Perfect, thank you. Yeah, but I was involved in the production of our guidance on safety critical task analysis, and many of you might be familiar with that because it's become in some ways the de facto standard on safety critical task analysis used in many parts of the world, from I know it's used in Brazil and Singapore, and everywhere in between. So let me just introduce myself and the Energy Institute. So I've been with the Energy Institute for about 14 years now, and in that time I've managed human factors committee, and all of the various guidance documents and other resources that we've produced. And I'm not going to talk about all of those today. I'm going to talk about one of those, and that's around safety critical task analysis. Let me just get the slide going. There we go. So just very briefly about the Energy Institute. If you're not aware, Energy Institute is a professional membership body for the energy sector. So unlike IMechE, who are there to support mechanical engineers, we're here to support anyone really who's working in the energy sector, regardless of what their role is. Whether you're an accountant, could be an engineer, could be a petrochemical engineer, could be an energy manager, etc., etc. The Energy Institute is the home for those types of people. And as a professional body, we do the things that professional bodies do. So we're here about developing the future energy workforce. We've got we provide training, we provide events, and of course we charter people at various different professional membership grades. We're also here to essentially advise society. So the Energy Institute is a charity, and we're a registered charity because we are essentially an information charity. So we provide good science and essentially knowledge to wider society, to government, and to those who work in the energy sector as well. And then lastly, we're here to support industry operations. So a big part of what the Energy Institute is about is around supporting the energy industry to be safer, more efficient, essentially. And so we have a whole what we call a technical work program, developing good practice guidance, standards, etc., on a whole range of topics, from process safety to human factors to fuel quality, environment, hydrogen, power systems, offshore wind, etc. The whole breadth and depth of the energy sector. Just a few numbers, really. We've got about 750 or more good practice guidance documents on our website, many of which, including the human factors titles, are freely available to anybody. We have our technical work program, funds around $2.5 million of, I won't call it research, but development, good practice guidance, standards, etc. per year. And we've got about, and that work is funded by around 50 to 60 company members who we call technical partners, and they're many of the large energy companies, oil and gas, but also renewables as well. Right, so, well, stop the presentation. There's an incident alert. Okay, so let's have a look at this. So this, I found this on the Energy Institute's Toolbox website. There's about 700 incidents on there, and funny enough, this was the first one that I found. So this was the first one I looked at, and I thought, okay, it's perfect, probably to illustrate my point and what safety critical task analysis is all about. So we've got an incident here. We've got a unloading and loading operations. There have been several incidents reported related to loading and unloading of heated production fluids. Okay, so loading and unloading tankers, essentially. In one of those incidents, work was burnt when product escaped. And in others, there's been potential for spills and various other things, as you can see on the image there on the right. And importantly, the text in bold there says, so this type of incident occurs when the truckload line is disconnected before the production valve is closed and residual pressure remains in the line. Okay, so quite straightforward. The truck is connected to the whatever the truck's connected to, the product tank, and the line has been disconnected before the valve has been closed. It's a bit like, I don't know if you can do this actually, because there are safeguards, but imagine taking the petrol pump out of your car and then managing to sort of squirt petrol all over the place. But I don't think you can do that because there are safeguards. In this case, there aren't, and of course that means that when the line is disconnected, fluid escapes, and because it's heated fluid, can come in direct contact with the worker, causing burns, and of course can spill into the environment. Now, if we were to look at this using something like a Swiss cheese model, we would say, well, on the left-hand side there, we have a hazard, and that hazard is heated production fluids, okay, currently in a tank, okay, so the hazard is controlled. We have a potential incident on the right-hand side there, so potential for spills, potential for injuries, burns, etc. And the thing that can release that hazard from the tank is a task, okay, or in this case, a business need, we could call it. So we have a need to load and unload production fluids to and from the tank, okay. Now, to manage that task, we have various steps. So we break that task down into, let's say, 5 steps in this case. We could visualize some of those as barriers. They might not all be barriers, but we could visualize them as barriers and complete our Swiss cheese model. And if all those steps are done correctly, the incident shouldn't happen. Okay, very straightforward. Now, we've documented that step-by-step process in a procedure. Okay, we've trained the workers to to follow that process, that procedure, and we think, okay, great, job done. That's all that needs to happen. But as we saw from the incident alert, things can go wrong. And so if we look more closely at the 5 steps there on the screen, we see that, well, one of those steps is fairly critical, okay, to this task being done safely and correctly. So step 3 is close the production valve before disconnecting the load line. Okay, and we know from experience, from the incident alert, that when that doesn't happen, the incident happens. Okay, the product spills, someone gets injured, someone gets burnt, or product leaks all over the floor. Congratulations, you've just discovered a safety critical task. Okay, so what is a safety critical task? So a safety critical task is a task where human factors could cause or contribute to a major incident. It could also refer to a task where human factors could disrupt the mitigation of that incident. And so safety critical tasks can be operational tasks, they can be emergency response, they can be control and mitigation tasks, it could be various different types of tasks. The important thing is that a safety critical task is not just a task where someone can get hurt. And I know in the US, this has caused some issues, or at least quite a long time ago when I was talking to people there. In many companies there's this consideration: oh, safety critical task. That's any task where someone can get hurt or injured. Climbing up a ladder, do anything like that. Okay, no, that's not it. Unless that person climbing up the ladder is holding the roof up or something, it's not a safety critical task. So a safety critical task is where a human action can cause a major incident. Okay, that is what it is. It's not just where someone can get hurt, and that's why I think this diagram on the right is quite useful to visualize that. So safety critical task analysis then is a qualitative assessment of a safety critical task. It's not a quantitative assessment. So if you do LOPA studies and things like that, we're not trying to give a probability of something going wrong. It's qualitative. So what this really means is that it's all about breaking down a task. So we take a task that we think is safety critical, we break it down into subtasks or steps. It's the same thing. And then we want to understand, okay, well, each of those steps, what human errors can occur? What would the consequences be of that human error? And what are the error traps that make that human error more likely? So error traps is a term that some people like, some people don't. Others would call it performance influencing factors and things like that. But I think error traps kind of gets the point across quite nicely. And of course, at the end of the whole point of safety critical task analysis is to make is to recommend changes to remove the error or to reduce the error likelihood by removing the error traps, making the task inherently safer, and ultimately we want to reduce risk to as low as reasonably practical. And importantly, safety critical task analysis is quite a major undertaking. There are simpler types of human factors analysis that can be done that I will mention at the end, but safety critical task analysis is really, it's equivalent to a HAZOP, so it's quite an undertaking, and therefore it only really needs to be done for the most serious process safety risks. So there are 7 steps in a safety critical task analysis, and I'm going to talk about each one very briefly, and then I think Richard's got an example safety critical task at the end to show you. So step 1 is around identifying the main hazards. So as I said, I'm going to call it SCTA is for the largest risks that we have, the most risky tasks that we undertake. And so ultimately the first step is understanding, okay, well, what are the things that really keep you awake at night? What are your major hazards on site? And of course this is going to vary site to site, but obviously on a refinery you're going to have oil and various oil products. On a nuclear site you've got the nuclear reactor, of course, and radiation hazards. And so whatever your site is, you've got to decide, okay, what are the main hazards? And then the next step, so step 2 is around prioritizing the safety critical tasks that you want to analyze. So this is probably the main stage where companies struggle. So a typical large site might have thousands of tasks, thousands and thousands of tasks that are undertaken. And of course, not all of them need to have an SCTA done on them. And so companies struggle to understand, okay, well, which ones do? Which ones do I need to analyze, and which ones don't I need to analyze? And that's usually the first major step that needs to take place. There's a few ways that companies can prioritize the tasks they need to look at. I mean, ultimately, they want to concentrate on only the most safety critical tasks. So how do we find that out? Well, often there could be it could be the subject of incidents in the past. So if you've got incident reports, it's quite possible that there may have been some tasks or example tasks in there that could be considered safety critical. That's one way of doing it. Another way is, I mean, the ultimate thing is to think what tasks, when not done correctly, can release the hazards, and which tasks have the most human involvement. And so you can essentially use a sort of a screening exercise, like shown on the right-hand side there, in order to sort of try and prioritize tasks by level of human involvement and the consequences if things go, if things go wrong. One of the problems that companies often have is they either cast the net too wide when trying to prioritize safety critical tasks, or they cast it too narrow. So, for example, you don't want to just necessarily look at every loading operation, because loading could involve loading a tanker, but it could involve loading boxes on the back of a van. So that's obviously far too wide to look at. But of course, you don't want to look at every single turn of a valve that takes place on that site. So you don't want to be so specific that you're analysing, every task possible that includes valve turning. So there is a bit of an art to it, I suppose. And as I said, using screening tools can help you. Example tasks, though, would be shown on screen. So you have initiating tasks, preventative tasks, mitigation tasks. So often things like import and export of materials, those are often safety critical tasks, depending on what the material, of course, is. Startups and shutdowns, preparing for maintenance, reinstatement of maintenance. Reinstatement after maintenance. Calibration of trips, responding to an alarm. So of course, depending on what the alarm is, that could be a highly safety critical task. Responding to a fire, responding to a leak, etc., etc. So these are example tasks. Now, once you've prioritized your tasks, you have to pick one. Okay, so you don't analyze them all at the same time. You analyze them one at a time. And so we focus on one of the identified safety critical tasks, and now we really need to understand how the task is done. Okay, and to do this, we don't just look at the procedure, because the procedure tells us how work as imagined is done. So the procedure is how we imagine the job to be done. What we actually really need to do is talk to the operators, carry out a talkthrough, as well as looking at the procedure, in order to understand really how the work is actually done. Okay, and that's why they've got this triangle on the right there. Examine documents, interview personnel, interactive observation, and using this, hopefully we gain an accurate understanding of how that task is actually done. Step 4 then is around describing the critical subtasks in that task. So it's worth just sort of saying that a task in this case is a fairly high level description of a whole series of activities that need to go on. So, for example, I mean, the way I would probably think about it is, if you've got a procedure on carrying something out, that the procedure is probably the task, and then the different steps in the procedure would be considered the subtasks. So we can use a hierarchical task analysis to visualize a task. So we start off with high level subtasks. So in this case, this is well, I put this one together. It's not a real one, but it's just sort of one I put together to sort of quite simply illustrate the incident that we talked about at the beginning of the presentation. So this is the loading tanker fluid into a tanker. So we've got 3 main subtasks: connect the tanker to the vessel, load the product, and then disconnect the tanker from the vessel. And there could, of course, be other tasks involved in this as well, but these are the three I chose to include to illustrate the point. And then, of course, we might decide that connect tanker to a vessel is a fine description of what needs to happen. We don't need any more explanation. Or we might decide actually there are a number of additional sub-steps involved in making that subtask happen. So we break it up into further points. And this is quite easy. I did this in PowerPoint, just using the smart art function. So you don't need necessarily special software to do this, but understand that there is special software available that you can purchase to make this easier. Okay, so once we're happy that we've got a fairly accurate and useful picture of the task, step 5 is all about identifying what can go wrong and what could make it go wrong. Okay, so we identifying potential errors and error traps, or performance influencing factors, or PIFs for short. So if we take a look at subtask 3, disconnect the tanker from the vessel. I mean, that's a task. That's a subtask that we know has gone wrong in the past. Okay, because we've got the incident alert to prove that. So we look at this. Whilst we would obviously look at all of these tasks, just for illustrative purposes, we're just going to look at step 3 here. So disconnect the tanker from the vessel. You can see that we've got 3 subtasks there. So close the product valve, disconnect the load line, and then stow the load line. So what errors could be made during this subtask? And the way, this isn't necessarily the only way to do it, but this is the main way that is done, that is used. For each of those steps, we can apply a series of keywords. So it's just like doing a HAZOP in many ways. In fact, we often call it a human HAZOP. So you can see there we've got action errors, check-in errors, information retrieval errors, selection errors, etc., etc. So different types of errors. And then we can look at them, one by one, and say, well, could this operation be done? Could it take too long? Could it be done, be done too quickly? Could the operation be mistimed? Can an operation be omitted? And you can see there that it doesn't only apply to actions. If it's a check, so having to check a gauge, perhaps it means to check the level on a gauge. Again, can that check be omitted? Perhaps we don't check everything that we need to check. Perhaps we check the wrong gauge, so right check on wrong object. Okay, so using this, we can, in a very robust and methodical way, look at each step and understand, what are all the potential errors that could go wrong. And there might be only one error that could be made. There might be half a dozen. Okay, but the point is, we need to consider them all. Now, as I said, once we've identified an error, so I've got one here. So for step 3.1, close the product valve, we've identified A9, operation omitted. So the worker can disconnect the load line before closing the production valve. So whether you want to call this action omitted or done in the wrong order or something like that, it doesn't really matter, but we've identified the potential error. Okay, so now that we've done that, we need to identify, okay, well, why might this error take place? In an ideal world, this sort of error shouldn't be possible, of course, but of course it is. So why is that likely? So to do that, this is where we need to consider error traps or performance influencing factors. And when you can see here, this is just a list of potential error traps. This doesn't, I don't believe this exists in the safety critical task guidance as such, but there are many different frameworks that can be used to consider different types of error traps. Often a good way of doing it is to consider, break things down into errors, traps to do with the job, the person, or the organization, or sometimes the task as well. So if we look at this, what might make this particular error more likely? So, for example, if it's a very routine job, which I suspect in this case it probably is, Those sorts of tasks tend to be done without thinking. You know, operators just do them. It's a bit like driving a car. You know, and you know, we are fallible, and those sort of routine tasks, you know, we sometimes do things in the wrong order, etc., miss things out. So that could be a potential error trap, because this is highly routine. Time available or time required. So if there are time pressures on the operators, which again I suspect there are, perhaps there are bonuses for doing all the deliveries to time, or maybe there are other time pressures as well. That can of course make people either rush, you know, either take shortcuts, you know, deliberately, or of course make mistakes. If we look at the person as well, there may be physical capability issues. You know, if there's a valve that needs to be turned, and perhaps it needs two people to turn it, perhaps rather than one. Perhaps people overloaded or even underloaded. You know, these can affect people's attentions, affect people's ability to you know, remember each step in a procedure, etc. And of course, when we look at the organisation as well, there could be staffing pressures. So again, perhaps this is a task that needs two people, and there's only one available, and maybe that's a potential error trap in this case. Okay. Now, what we do in safety critical task analysis, and this is what makes one of the things that makes safety critical tasks such a robust technique, is we complete a table. So all these different things I've been saying about, you know, the subtasks, understanding, you know, the different subtasks, understanding the potential errors, the potential error traps. We need to keep a record of all that. Okay. And we do it in a table, something like this. So you can see on the left there, we've got the current arrangements that we have in place. We've got the subtask, and you can see I've put step 3.1, step 3.2 there. The potential error, which I've talked about. Various different error traps. So, you know, procedures being unclear, procedures not being available, etc., etc. These aren't necessarily error traps that do exist. There could be error traps that could exist, but obviously we want to identify the things that, you know, are currently in place. And you can see there as well that one of the error traps is the design of the nozzle. Or, you know, as I said, I mean, in this case, the workers can physically remove the line from the, you know, from the truck, even if it's under pressure. Okay, and obviously, if the nozzle allows that to happen, if the design allows that to happen, then it can happen. Of course, that becomes an error trap as well. I won't dwell on this too much because I know Richard's got a real example to show. But you can see there that we've got, you know, we've got potential errors, error traps. We can identify the existing safety measures and recovery options, so that if the error does happen, you know, is there something that can, you know, can we recover from that and go back to you know, a normal situation. And of course, we've got the consequences as well if not recovered. In this case, loss of containment, burns to the operator. Now, step 6 then is, so once we've identified all the different errors and error traps, we need to think, well, what are we going to do about that? Okay, what can we improve? And so on the right hand side, we have the potential improvements. So we have ways to reduce the errors, you know, or remove the error traps or reduce the errors. We have additional recovery measures that we could put in place. And what we probably should do is, for every task and every type of error that we identify, is we should consider using some sort of hierarchical, you know, hierarchy of risk management in order to try to address each of those. Okay, so as I said, it's just done very systematically. This is one on the left. I don't know if this is a real acronym or something I probably made up, but I've called it Rambo. Remove, can the hazard be removed? Automate, can the human contribution be removed by automating the system? Mitigation, so can the consequences of human failure be prevented? Bar is essentially, can the human performance be assured by mechanical or electrical means. So in this case, for example, if it was impossible to remove the nozzle from the truck or from the tanker whilst it was under pressure, then of course that would probably solve the incidents, barring assuming there wasn't a design fault or something with the nozzle. And then the last one is optimized workplace. So, can the error traps be removed, and optimized? Can we provide more time for a job? Can, better lighting, improve supervision, etc., etc. And you can see there on the right that I've included, I've tried to include something that considers all of these points just for illustration. So, and you can see again on the right hand side, we have space for comments. So the purpose of safety critical task analysis is to get the risk down to as low as reasonably practicable. So that means that it doesn't mean identifying completely outlandish and impossible things that we can't implement. So for example, could we get a robot to drive the truck and fill the tanker and no, okay, that's not really practicable. Can we get the operator wear PPE whilst carrying out the task? Okay, we can do that. It's not the best option because it's a recovery measure. Can we replace, can we introduce some sort of nozzle with a lock-in design so that it can't be removed under pressure? Yes, we can do that. Okay, that sounds very reasonable, and that's probably the main recommendation that we could make. And of course, another one down there is carry out the activity in pairs to include some sort of check-in mechanism in the task. Now, step 7 is that we need to implement and monitor the changes. So there's no point doing this exercise if we don't actually then make changes off the back of it. So we need to take the results of the safety critical task analysis, make changes to equipment, update procedures, maybe introduce new training courses, communicate those changes. And of course, this should be done under management change process. And ultimately, we need to also check the effectiveness of those changes, talk to the operators, collect data, etc., to make sure that the changes we've made are actually improvements. Now, as I said, safety critical task analysis is a major undertaking. Okay, you can see this table here on the right hand side there. It involves really human factors experts being involved in that, plus members of the workforce, plus health and safety, health and safety environment experts, HSE specialists. It typically takes 1 to 3 days to analyze a single task. Okay, so these things tend to be done in big batches, lasting a few weeks or longer at a time. And it takes about 5 days to be trained up in the methodology, effectively. So it is a major undertaking, and of course, it's for the most major accident hazards. Okay, so it's one of those things that is worth doing and worth doing well, but it does take a long time. However, the principle of understanding what errors can be made, understanding what traps exist, and trying to do something about those error traps is something that actually can be integrated into other types of risk assessment much further down the line, much closer to the front line. And that's actually the focus of a current project that we're developing in the Energy Institute at the moment. But the general process of identifying error traps can be integrated right at the front line if you want. Carrying out a 10-minute observation of the workplace to see what error traps are present, or integrating it into job safety analysis or at the permit to work process as well. So I guess in summary, so understanding human factors is a key part of process safety management. And one way to do this is understanding our most at-risk tasks, which in this case are those with high consequences and high human factors involvement. We break down the task into steps to understand what can go wrong, what error traps will make it more likely to go wrong. We implement changes to the task or the work environment to either remove the hazard, remove the human, support human performance by removing the error traps, or reducing the consequences to make recovery easier. As I said, safety critical task analysis is probably the most robust way to do this, but it is a major undertaking, and there are lighter ways to do it as well for less critical tasks. What's the benefit for coma sites in the UK? Carrying out safety critical task analysis meets the HSE's expectations. Okay, but more broadly than that, should be a reduction in risk, avoidance of major incidents, and we're talking about company-ending incidents. Okay, as well as obviously life-ending incidents and you know, major damage to equipment. But these are potentially ruinous to an organisation. More efficient tasks, happier workforce, reduced error traps, reduced non-compliance, you know, reduced errors as well. Energy Institute provides guidance on carrying out safety critical task analysis, and you can see up there on screen for the massive price of £0 and 0 pence. That's completely free guidance document. Training is also available. I think we deliver a training via the Energy Institute, and other organisations do as well. So you can see that there, checking out our website if you're interested in that. Okay, so that's me. Richard, I've got your slides. Do we still have time for you to have? I realise I went a bit over time there.
Okay, that's fine. Thanks, Stuart. I'll actually share my screen if you don't mind.
Yeah, no problem.
Because I've made some couple of tweaks. So hopefully you can see my front slide, everyone.
Just your desktop at the moment.
That's probably the wrong one then. Let me just share the right one. Go for that one instead.
Yep.
Yeah, all happy? Right. So I'll give you an example then of SCTA at a coma plant. And just to explain, at the time I was responsible, senior engineer for a coma plant in England. So we had our safety cases, etc., etc. So, and it was at the time when the HSC was starting to ask about human factors. So we decided to go and do SCTA. And a sort of slightly different view to Stuart on some of this. I think this can be really simple. I don't think it has to be too complicated, and I'll explain that. But the first thing is you have these tasks, and we had lots and lots of tasks. I'll show you in a minute. We scored them, but we put some numbers on because I know it's qualitative, but it can be a bit too qualitative. So we found it easy to give it a score. And when we said it's safety critical, we meant it would realise a major accident hazard as listed in our coma safety report. So in general, that was a release of highly flammable hydrocarbons that could fire or explode, or something that would gas you and kill you pretty quickly. So that's the sort of level we were pitching it at. Clearly, if you're in the rail industry, it'd be something else entirely. And the same thing with the amount of involvement. And about 90% of our jobs were run through DCS, through distributed control system, but there was usually a human element, and there were some jobs that were completely human, both in operations and maintenance. So that's the scoring mechanism. So we then only did SCTA on the red ones, the 24s and the 36s. Now, this isn't the full spreadsheet, but there were 275 on this. I've just sort of shown some of the red, orange and green ones. 275 tasks were checked, scored by the operators, not by the managers. So we got one or two good operators, experienced ones. We sat them down and we said, well, what jobs do you do? And technician as well, not just the ones that are written down in our operating manuals, because that's sort of what we envision being done, but what's actually done. Just tell us the title, even if you haven't got a procedure for it. What are you done? What do you do? So we listed them all, and they scored the amount of human involvement and the potential. Just to give a bit of a clue on this, VCM is vinyl chloride monomer, very, very flammable. It's a bit like LPG, but it's also a carcinogen, so you'll see it throughout. But the whole bunch of things, I'll come back to this yellow one in a minute, you know, dropping an ammonia cylinder, hot work, leak testing, pressure testing, removing valves out of reactors, thermal expansion due to use of steam hose on a monomer. There's loads and loads of things that could cause this loss of primary containment, which is the main thing we're trying to avoid through process safety management. I'm not going through all of these here. But I thought it is interesting, though, because we might have a diverse audience, to pick up on one thing that's perhaps common across all industries, responding to alarms. So it's not opening and shutting valves or disconnecting something, it's just responding to alarms. So I'm going to pick up the SCTA just on this one example. And I'll give thanks to Paul Harley as well, colleague and friend, who's a Portman Risk consultant. At the time, he facilitated this SCTA and some other ones. So controller and operator fails to respond to a critical alarm. So a bit of background, central control room, lots of display screens and alarm panels all over the place. And it's a sort of was a general principle of the plant that we didn't want safety critical alarms. We would prefer instrumented trips, still rated trips, because they weren't independent. But so they're not safety critical alarms, but they were alarms up front to warn you something is starting to go out of control. And in most cases, depending on which alarm went off, if it was ignored or forgotten or not noticed or whatever else, although it might be a precursor to a major accident hazard event, in general, we had measures to minimise it through safety instrumented systems, etc. I'm not going to go through all the HAZOPs, obviously, because that's take all day. But so, all right, we've got an alarm. So the first thing is it critical or not? So using the human failure guide words, just like this is like a HAZOP node now, and this is the deviations list. Information not obtained or wrong information obtained. Well, where is it? Well, it's in his workstation, so that's okay. But we've got an alarm handling screen as well, and we located it within 30 degrees of his eye line, because there's no point being behind his back because he won't see it. But he's got a second screen as well, have a lot of things going on. Of course, the consequence depends on what the alarm is doing. But we did have an annunciator panel that was sort of located a bit further away, old-fashioned Ronin type one with the lights and the buzzers, and we were steadily moving them across. So we had a project to complete. And then you look at the poor presentation of that information, text size, font colors, etc., to make sure it's a consistent scheme that everyone understands. So that's the first task step, the identify critical alarm. The next task step is we'll respond to that alarm. So potential human failures, he doesn't respond, so operation not admitted, or he does something in the wrong order. So prioritization of alarms. Now, a lot of incidents, when they start to happen, you get alarm flooding. I had an incident at a plant a couple of years ago where one compressor tripped on particular gas. There were 100 process alarms that the compressor was tripping, most of them to do with reliability and other things, masking the fact that there was a problem with the scrubber, and there was actually a loss of containment from the scrubber, but they couldn't see it because of all the alarms. So it's important to prioritize the alarms, and you have this thing called IMechE 191. It's sort of fairly common in Britain. If you haven't got it, you should get it. There are also American codes that do the similar thing. It gives excellent advice how to do that prioritization, and lots of other things to do with it as well. And then the availability of alarms. Well, what we did is we took all, not just alarms, but messages that came up in the DCS, fire alarm, pumps on a different panel, all these things, put them in one place so that we can have a consistent availability. Again, that involved field wiring and various other things that needed to be completed. Location and availability of alarm information. So we had an alarm handling screen following IMechE 191 codes with color coded and prioritized, etc. I'm not going to go through all of this. And then with the alarms, for the priority alarms, if you click to acknowledge an alarm, it popped up with a PDF of what to do. So you didn't have to rely on memory and training when you're panicking. There's a PDF with all the priority alarms attached, so they immediately have the response. So we needed to complete that. And then moving on to the sort of more about the PIFs, the influencing factors. There's 2 pages of this. Ability to manage the workload presented by the alarm system. So again, about the interface, control room operators trained in the key responses and what to do, safety instrumented systems backed up, blah, 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 blah. Alarm flooding, I talked about that, so we'd rationalised that already. Prioritised, priority 1 and 2 alarms are distinct and audible to attract attention. The lower priority alarms, different colours, less in your face, less noisy. So you just start to go down it. And the point is, this wasn't run by me or Paul as a sort of expert HF engineer or scientist or a manager. This was run by the operators, for the operators. All your job is to facilitate them. They have the answers, just need to write them down. Communications, were the radios good? Do they work okay? Because in some places it's really noisy. Does the alarm go to the radio so they're alerted if they're out in the field rather than in front of the control panel? Making sure the environment is okay, there's no glare on the screen, the noise levels are okay, blah, blah. All these things to make it obvious that an alarm's happening. The people, well, it's not a physically demanding job, so that's not so bad. 12-hour shifts, yeah, fatigueness is perhaps a big issue then, or could be a big issue. We've sort of got the working time directive in Europe and the UK still, so that limits us, but in the States, not so much. I think if you look at the Texas City refinery, I think they had a guy did 30 12-hour shifts in a row before that happened. You can see how fatigue's an issue. So, and then then you carry on with the person factors, stress, morale, is that an issue? Because it does affect things. It has a huge effect. If someone's bringing to work the stress or the problems they've got at home, that can be a problem. So we need to keep on top of that. Not that we can do much about it other than keep on top. And the second, workload overload, of course we can. That's down to management. Richard's already mentioned that. It's organisational change can be a problem. And then competence. Competence is vital. Good onboarding and keeping people up to date with what they need to know. And also staffing levels as a work factor. In this particular plant, we operated with a single operator on the panel, but breaks were covered by someone else who's quite capable of running it, and they did a handover. And making sure that the alarms and the radios work when they're away, that was fine. So that's just one example of that task of responding to an alarm. There's a few links here from the COMA Competent Authority. Two of the links that really Stuart's already mentioned about some training, but they aren't the only providers. RiskTech, who are part of TUV, used to be part of ABB. They are pretty hot on this. They've got training courses. Human Reliability Canada, they've got training courses. You can get special software if you want it. Have to pay for it, of course. And also, if anybody actually wants it, freebie from me, just email me. I've used my own spreadsheet which is really aimed at the operators. You've got all in really easy speak, the tasks on the front. Then you split your task down to subtasks or steps, and then stick them in, and then select from your drop-down lists. So it's actually pretty, in my opinion, pretty straightforward, and you can do it fairly quickly. I think the important thing is this area, when you need to start grouping some things together. So loading and unloading road tankers or rail cars, that you can group them together, because you should have the same level of checks and balances really on those things. And things like 4 eyes principle is the classic. If you get someone, say, when you've done it, you have to get someone else to countersign the form to say you've done it. People pay attention. So sometimes 4 eyes is very useful, because it just gives you a bit more of a layer of protection. So really that's it from me. As I say, I will pop these resources up just on the screen for a minute while I'm finishing off that talk. It can be a really simple technique. If you've done HAZOP or any other FMEA or any other risk assessment, it's basically the same stuff. But the really good thing about this is If you ask about human error and failure, people get the backs up and they go defensive. This is completely dispassionate, and if you get the operators to lead it, they will volunteer stuff that can go wrong. If you lead it, not so much. So it's really important to involve the team, and they will run it for you once you get going. That's it. Just one
Okay.
example. I'm done.
Great stuff. Thanks, Richard and Stuart. Actually, that has not yet prompted any questions. If anybody has questions, now would be a good time before we stop for coffee. I will also say that between Richard and myself, there are various links to other resources, and we will try and get those into the chat before the end of the meeting so that you can actually click and follow those links, anybody who's in the meeting.
If anybody wants that spreadsheet, by the way, I'll just pop my IMechE email address in the chat. I'm happy to send it to you afterwards.
That's very kind. But questions around the idea of safety critical task analysis and the examples that Richard has given? Any thoughts on where it might also be applied? Interesting point from Stuart that depending on how complex an approach you're going to take, you might want to reserve it for the most critical tasks rather than everything. But the concepts of performance influencing factors, or error traps, as Stuart referred to them, I think are very relevant in all sorts of risk assessments, and particularly risk assessments of what seem to be simple jobs but are heavily human reliant. Okay. Well, I've given people time to get their fingers on the keyboards, and they've not taken it. So what I'm going to propose is that we take a 15-minute break now. So at 11:35, I'll pop back up and we'll get our next session underway. So take an opportunity to get caffeine or whatever it is you want, and we'll go from there. See you shortly. Hello again, everyone. Hope you're doing all right. Hope you've managed to fill your cups, do whatever it is you need to do. Welcome back to the second half of the webinar. Just before we move on to the next session, let me just note to everybody that Richard has put his links into the chat. So if any of those links associated with critical task analysis, human failures, and so on are of interest to you, you can follow them directly, or no doubt bag them and copy them out. Just saves you a bit of time. Let me just check whether there are any further aspects in Q&A. No, nothing in Q&A. So for the next session, we are talking about decision making at the professional engineer level, perhaps, and especially with respect to safety and environmental protection. That decision making can be thrown into stark relief by incidents and when incidents occur. That said, almost all of the decisions that we make as professional engineers go without any hitch at all. But having said that, we should reflect a little bit on what could be the outcomes of our decisions. And with that in mind, the next session is going to look at a number of case studies. Pamela, Tim, and Richard are going to go through a case study each, and we will be wanting your input and your views as we go along. So Q&A again, chat if necessary. We're going to look at a couple of case studies. We're going to look at whether organisations have appropriate frameworks for raising concerns, and a little bit at the need to apply lessons. But Richard will close the session with some thoughts from various professional engineering institutions. And it is kind of important to note that if we are members or associate with a profession, then we will be judged by our peers through that professional engineering institution, or at the very least by our peers in retrospect. So I wonder if Richard, Pam and Tim could pop up on screen, and then I can hand over and let you get on with the session. Hi, Tim.
Hi, thanks, Richard.
There's Pam. Okay, so let me just hand over. You guys can do a quick bit of introduction, and then I'll follow the session and make some notes for my roundup a little bit later, and I'll speak to you later.
Yeah, I guess I'm first. So my name's Tim Jones. Been with the IMechE for around 20 years now. Sit in various committees. So my background is process safety, more on the quantitative side, so kind of fire and explosion modelling. Pam, do you want to go next?
Thank you. Yeah, I'm Pamela Robinson. I again have been with the IMechE 20 odd years probably now. Probably too many. I work in the water and wastewater industry, and that's my background. And process safety associated with water and wastewater. I'm also a member of the Water and Wastewater IMechE TAC Committee and the Northwest Process Division, which is why I've got into this here today. Thank you.
You've already seen me, haven't you? But nowadays I lead process safety in the Westlake group, which is mainly chemicals, covering, in my case, I have 18 plants spread across Europe and Asia that I have involvement with. But I also get involved with various NGOs and trade associations and other things as well.
Okay, so yeah, as Richard said, this session is largely around presenting kind of 3 case studies. So if you have any questions as the case studies are presented, like I say, feel free to put them in the chat. And then at the end of the session of the 3 case studies, then Richard's got some summary slides around the kind of decision-making process as a professional engineer, and then we'll hopefully have some discussions on those case studies as well. So yeah, I'll just share my screen and get the first one going. Yeah, so the first one is an explosion that happened at the Formosa plastics facility in the US, which was a PVC manufacturing facility. So can you see that? Yeah.
Yeah, it's clear.
Yeah, I can see it.
And
I can't hear anything.
yeah,
I can now.
On April
Working now.
23rd, 2004, an explosion at the Formosa Plastics Corporation facility rocked the small town of Illiopolis in central Illinois. 5 workers died, including a husband and wife. 3 others were severely injured. Authorities evacuated approximately 150 residents from the area. The incident had serious economic consequences for the surrounding community as the plant did not reopen. The facility, which employed 139 workers, produced PVC, a common plastic. PVC is used to make many different products, including credit cards, clothing, pipe, siding, and flooring. Borden Chemical constructed it in 1965, and Formosa purchased it in 2002, 2 years before the accident. The CSB investigated the incident and issued a report with findings and recommendations.
This explosion occurred after a worker opened a valve on a pressurized reactor full of flammable material. It might be tempting to simply blame the tragedy on human error. However, as is often the case, the root causes were much deeper.
The CSB investigation revealed that better operating practices and equipment design could have reduced the chances of human error that had such catastrophic consequences. The CSB used physical evidence, documents, and the testimony of the few surviving witnesses to reconstruct the accident. The following computer simulation shows how events likely unfolded. The Formosa plant made polyvinyl chloride, or PVC, in 24 large vessels called reactors that were arranged in groups of 4. Inside each vessel, thousands of pounds of highly flammable, toxic vinyl chloride reacted under heat and pressure to form PVC. An operator controlled the process from a panel on the upper level. When the process was finished, a second operator would walk down the stairs and open valves on the reactor piping to transfer the product out. After completing the transfer, a worker back on the top level would then clean out the inside of the reactor with a high-pressure water blaster. The worker would then go to the lower level and open the reactor bottom valve as well as the drain valve. Water emptied onto the floor into a drain. On the evening of the accident, an operator started cleaning reactor 306 with the water blaster. He then walked downstairs to drain the water out of the reactor that he had been cleaning, but he made a critical mistake. The CSB concluded that instead of turning left at the bottom of the stairs to get to reactor 306, the operator turned right to a different group of reactors and approached reactor 310. But reactor 310 was not in the cleaning process. It was pressurized and heated in mid-cycle, making PVC. The operator turned switches to open the reactor bottom valve and the drain valve. The drain valve opened, but the reactor bottom valve remained shut. An interlock blocked the air supply to the valve's actuator. It was designed to do this as a safety measure when the reactor was under pressure, to prevent an accidental release. But instead of checking to see why this valve would not open, the operator decided to bypass the interlock. He disconnected the existing valve air supply hose and reached for one with a continuous air supply meant for use only in emergencies. He connected this hose to the valve. It opened. Suddenly, the highly flammable vinyl chloride mixture began rushing out onto the floor, producing a loud rumbling noise that sounded to witnesses like a jet engine. Workers smelled vinyl chloride, and the vapors triggered an alarm. The shift supervisor rushed toward the reactors. There he saw reactor 310 spraying vinyl chloride onto the floor, where there was already a foaming mixture 1.5 feet deep. Believing he could stop the release, the supervisor raced to the upper level and told operators to open valves, which would relieve pressure in the reactor. The supervisor and one operator then tried to get to the lower level through an interior stairwell, but were stopped by the overwhelming odor of the vinyl chloride vapor. The operator remained on the upper level. the supervisor headed down to the lower level on an exterior stairwell. Just then, the vinyl chloride ignited and exploded violently. Witnesses reported 3 or 4 additional explosions. 4 workers were killed immediately. The 2 operators who had been working at the top of the reactor and 2 operators who had been on the lower level, including the one who had apparently opened the reactor bottom valve. A 5th operator, who was seriously burned, died 2 weeks later. 2 other workers and the supervisor, who had been in the exterior stairwell, were seriously injured. The force of the explosions destroyed much of the plant, including the laboratory and the safety and engineering offices. It blew off the reactor building roof, knocked down walls, damaged metal frames and piping, and lifted the reinforced concrete floors on the upper levels of the plant. The CSB investigation found that systems and procedures put in place by both Borden Chemical and Formosa were insufficient to minimize the potential for human error. Formosa did not adequately train and drill its employees to immediately evacuate in the case of a major release of hazardous chemicals. Such an evacuation would have saved lives.
One way to minimize human error, the CSB found, would have been to install additional locks or other devices to prevent critical valves from being opened when the reactor was under pressure. Overriding the only safety interlock was all too easy to do by simply attaching the emergency air hose that hung nearby. Although the reactors were clearly numbered, they were grouped into similar sets of 4, increasing the chance that an operator might go to the wrong reactor. There were no gauges, indicators, or warning lights to inform operators on the lower level that a reactor was processing vinyl chloride. And those operators did not carry radios or have an intercom, so they were unable to quickly check on the reactor status with operators at the controls upstairs. In 1992, Borden Chemical, the previous owner of the Iliopolis plant, conducted a process hazard analysis which stated that the interlock on the reactor bottom valve was susceptible to misuse. Additional safeguards were recommended, but never adopted. Another hazard analysis in 1999 again identified severe consequences if someone opened the bottom valve on an operating reactor. But the analysis incorrectly concluded that the existing safety interlock was sufficient to prevent a serious incident.
Companies need to thoroughly investigate near-miss incidents to uncover any underlying trends or safety weaknesses. Formosa experienced several previous reactor incidents that, taken together, could have pointed to the potential for catastrophic consequences from human errors. In 2003, an operator at Formosa's Baton Rouge, Louisiana PVC plant opened the bottom valve on the wrong reactor, releasing 8,000 pounds of vinyl chloride to the atmosphere. In February 2004, an operator at the Iliopolis plant bypassed a reactor bottom valve interlock, resulting in another significant atmospheric release of vinyl chloride. Formosa then recognized that additional controls were needed, but didn't act quickly enough to implement improvements. The explosion occurred 2 months later. When a large chemical release like this occurs, employees need to get out of harm's way as quickly as possible. Companies need to train and drill their employees to evacuate instinctively. In this case, 2 operators remained on the upper level, trying in vain to slow the release. They and others who remained in the area died in the explosion. Their lives would have been saved had they evacuated immediately.
The CSB identified many ways that the companies involved could have avoided this tragedy. To prevent future accidents, the CSB made several safety recommendations to the company, the EPA, the leading industry association, and others. The CSB recommended that the Formosa Corporation review the design and operation of all its U.S. facilities. The CSB urged Formosa to ensure that chemical processes are designed to minimize the consequences of human error, improve control of safety interlocks, more thoroughly evaluate high-risk hazards, consider all consequences in near-miss investigations, and improve emergency actions, including prompt evacuations with periodic drills. This accident occurred because the companies involved did not look closely enough at the potential for catastrophic consequences resulting from human error. People do make mistakes, and that is why it's all the more important to design systems that take into account the possibility of such errors. Thank you for watching this CSB safety video. To obtain a copy of this video and the full investigation report, please visit our website at www.csb.gov.
Okay, I'll now pass over to Pamela to introduce the next video.
And just while Pamela, you're just setting it up, I'll put the links to the 3 videos in the chat afterwards, so you can go and look at them at your leisure afterwards.
Hopefully you can see my screen.
Yeah.
And hear the music.
At 7:15 p.m. on February 7th, 2008, a series of violent sugar dust explosions devastated the Imperial Sugar Refinery in Port Wentworth, Georgia, just outside Savannah. Explosions raced through the buildings, fueled by accumulations of combustible sugar dust and sugar that had spilled from equipment. Thick concrete floors heaved up, and brick walls were blown into stairwells and work areas, blocking many exit routes. Fires spread rapidly. 8 workers died at the scene. 6 more died later at a regional burn center. Dozens of others were injured. The plant's massive sugar packing buildings were a total loss.
The accident at Imperial Sugar was the deadliest industrial dust explosion in the United States in decades. It highlights the extremely serious nature of combustible dust hazards.
There were significant accumulations of sugar dust and spilled granulated sugar on surfaces throughout this facility. Conditions were set for a catastrophic accident.
Imperial Sugar's sprawling Port Wentworth complex began operations in 1917 and grew to become one of the largest sugar refining and packaging facilities in the U.S. Granulated sugar from the refinery was stored in 3 100-foot-tall silos and then conveyed into packing buildings where it was packaged for distribution. Granulated sugar was also converted into specialty products, such as brown sugar and powdered sugar. Sugar was transported by a complex system of bucket elevators, screw conveyors, and conveyor belts. During this process, sugar spilled onto floors throughout the work area. In places, the spilled sugar was many inches deep. This sugar also contained fine particles, which became airborne. In addition, hammer mills were used to crush the granulated sugar into powdered sugar, creating even more dust. The machines were connected to a dust collection system, but it was undersized and in disrepair. And it was not connected to the bucket elevators and conveyors. Significant amounts of sugar dust escaped into the work areas. Workers routinely used compressed air to clean packaging machines, further dispersing sugar dust throughout the buildings. Over time, large amounts of dust accumulated on elevated, hard-to-clean surfaces, such as ducts, beams, and light fixtures. These surfaces were not cleaned often enough to always keep the dust below hazardous levels. In the tunnel beneath the sugar silos, granulated sugar flowed through chutes onto a long steel conveyor belt. From time to time, clumps of sugar would become stuck in one of the chutes, blocking the flow of sugar on the belt, spilling sugar onto the floor and releasing dust into the tunnel. But the tunnel was large and ventilated, so this airborne dust did not build up to explosive concentrations. However, in 2007, the company enclosed the conveyor belt with stainless steel panels to protect the sugar from possible contamination. The enclosure was not equipped with a dust collection system. As a consequence, sugar dust would now be trapped inside this enclosure. On February 7, 2008, clumps of sugar were found blocking one of the discharge chutes. Sugar from the adjacent silo likely spilled off the moving belt. Dust likely accumulated to an explosive concentration inside the enclosure. At about 7:15 p.m., the sugar dust contacted a nearby ignition source, likely an overheated bearing, and exploded. This primary explosion blew apart the enclosure and vented into the packing building. Accumulated sugar was lofted and ignited by the advancing fireballs. The dust clouds fueled a chain reaction of secondary explosions, which swept through the buildings. Concrete floors buckled, releasing tons of granulated and powdered sugar into the flames. Emergency evacuation drills had not been conducted, and the explosions had cut the power to much of the interior lighting. In the maze of darkened and damaged stairwells and passageways, workers desperately tried to flee the growing inferno. The CSB found that correspondence dating back to the late 1950s showed that plant managers in Port Wentworth were aware of the explosive nature of sugar dust and the danger of dust accumulations. As far back as 1961, a memo described a sugar dust explosion that heavily damaged the powdered sugar mill room.
Despite the long-standing awareness of the explosive nature of sugar dust, not enough was done to manage the hazard.
In 2006, the CSB issued a study of combustible dust, which called on OSHA to establish a comprehensive combustible dust standard based on the current standards of the National Fire Protection Association, or NFPA. In October 2007, OSHA began implementing a new national emphasis program to increase the enforcement of existing regulations related to combustible dust.
Imperial Sugar learned of the OSHA Combustible Dust National Emphasis Program 4 months before the devastating explosion at Port Wentworth. But management did not act effectively to control the serious dust problem in the packing buildings.
Less than 2 months before the disaster, an internal inspection showed that many tons of sugar were still regularly spilling onto the floors. This provided much of the fuel for the massive secondary explosions and fires. The CSB found that over the years, the Port Wentworth facility periodically experienced small fires fueled by spilled sugar and accumulated dust on equipment. But none resulted in a sugar dust explosion that propagated through the plant. Investigators said that decades of operating without a catastrophic explosion may have lulled managers into complacency. In its report, the CSB issued the following recommendations to the Imperial Sugar Company. Apply NFPA standards to the design and operation of the rebuilt Port Wentworth facility. Develop and implement comprehensive combustible dust control, housekeeping, and training programs. Improve emergency evacuation policies and procedures.
Companies can go a long way to control combustible dust within their own facilities by following the existing recommendations of the National Fire Protection Association. But it is also time for a comprehensive federal standard on combustible dust.
In April 2009, OSHA announced plans to begin rulemaking on a combustible dust standard for general industry. In its final report on the Imperial Sugar accident, the CSB recommended that OSHA move forward expeditiously with the new standard.
Without regulation, enforcement, and education, workers will continue to be at risk from catastrophic dust explosions.
For further information, please visit csb.gov.
Thank you for watching that. If anyone's got any initial comments that they want to be raised, want to discuss, please stick them in the chat. Just to summarise the videos you've just watched, that was an incident that happened in Imperial Sugar in 2008. The facilities had been open since 1917, so that's over 90 years of perhaps complacency as to the effects that dust can lead to. They did have a dust collection system, but it wasn't connected to everything, and it was in a state of disrepair, as mentioned. And then in 2007, they decided to cover that conveyor, as it showed in the video. And it wasn't long after that that an incident did occur. And then with all the secondary reactions due to the incomplete of cleaning operations that they did, and then unfortunately with the evacuation, it wasn't able to take place very safely due to internal power cuts, and internal lighting was deficient. So lots of things to think about and learn from, hopefully, and never repeat. So I'd like to, if there's nothing appeared in the chat, maybe one's for you to pick up, Richard, in the end.
Yeah, I'll no doubt come back to it. Hopefully you can see the flames on my screen.
Yes.
Yes.
Right, let's just see if the sound works as well. So this is a short one about a heat exchanger. Similar themes to what we've already seen, and I'll talk a little bit at the end. So let's try.
13. The Williams Geismar Olefins plant in Geismar, Louisiana. A heat exchanger violently ruptured, causing an explosion and fire that killed 2 workers. The Chemical Safety Board launched an investigation and issued a case study. In it, the agency describes a number of process safety management program deficiencies at Williams, which set the stage for the incident. In particular, the CSB found that the heat exchanger that failed was completely isolated from its pressure relief valve. When pressure inside the heat exchanger dangerously increased, there was nothing to stop a catastrophic rupture.
Our case study on the explosion at Williams describes an ineffective process safety management program at the plant at the time of the incident. We urge other companies to learn from our investigation, to incorporate our recommendations at their facilities, and to assess the current state of their process safety culture so that a similar accident can be averted.
The Williams Geismar Olefins plant is located in Geismar, Louisiana. The plant produces ethylene and propylene. These are chemicals used in the petrochemical industry to make a variety of products, including plastics and antifreeze. Within the Williams process is a distillation column called the propylene fractionator. It separates a mixture of propane and propylene. Heat exchangers called reboilers supply heat to the fractionator to boil the propane and propylene mixture, which is essential to the separation process. The reboilers are shell and tube heat exchangers. Hot water flows through the tubes, heating and vaporizing propane that flows through the shell and back to the propylene fractionator. The water that flows through the tubes contains a small amount of oily tar, which condenses into the water earlier in the process. Over time, the oily tar from the water builds up on the walls of the reboiler tubes. This buildup is called fouling. Fouling reduces the efficiency of the reboilers. Periodically, the reboilers must be shut down to clean the tubes. The original propylene fractionator design had both reboilers running simultaneously. But in that configuration, the fractionator had to be shut down when a reboiler fouled and needed cleaning. To prevent shutdown of the propylene fractionator each time the reboilers needed to be cleaned, in 2001, new valves were installed on each reboiler to allow for operation of only one at a time. The other reboiler is on standby, clean and ready for use. But unforeseen at the time, these valves introduced a serious hazard. They isolated the standby reboiler from its protective pressure relief valve, located on top of the fractionator. On June 13, 2013, during a daily meeting with operations and maintenance personnel, the Williams plant manager noticed that the water flow rate through the operating reboiler had dropped gradually over the past day. The operations supervisor informed the group he would try to identify the problem. He went into the plant to evaluate the water flow rates. The operations supervisor informed several personnel that fouling within the operating reboiler could be the problem, and they might need to switch the reboilers. He attempted to meet with his manager so they could get the necessary maintenance and operations personnel involved who would perform the work. But his manager was not available. The operations supervisor returned to the field. The CSB determined that at 8:33 a.m., the operations supervisor likely opened the water valves on the standby reboiler. Hot water began flowing inside. The valves blocking the reboiler from its protective pressure relief valve remained closed. But unknown to the operations supervisor, the standby reboiler contained flammable liquid propane that had accumulated during the 16 months the reboiler was out of service. The hot water quickly heated the liquid propane confined inside of the reboiler, and pressure dangerously increased. Just 3 minutes later, the reboiler violently ruptured. Propane exploded from the reboiler and ignited to create a massive fireball. The explosion killed the operations supervisor and an operator working nearby. 167 Williams employees and contractors reported being injured. During its investigation, the CSB found that prior to the explosion, the standby reboiler had been out of service for over a year, isolated from the process by closed block valves. But during this 16-month period, liquid propane unintentionally entered the shell of the reboiler, perhaps through a mistakenly opened valve or a leaking block valve. The CSB determined that when the operations supervisor opened the hot water valves to the standby reboiler, the propane liquid trapped inside was heated and expanded in volume to completely fill the reboiler shell. This caused pressure to dramatically increase until the reboiler ruptured.
When identifying overpressure protection requirements for heat exchangers, engineers should evaluate the scenario that caused the Williams explosion. The hot side of the heat exchanger was operated while the cold side was blocked in. In this scenario, just having a pressure relief valve available could have prevented the explosion.
The CSB discovered that in the 12 years leading to the incident, a series of process safety management program deficiencies caused the reboiler to be unprotected from overpressure. When Williams installed the process block valves on the reboilers in 2001, they performed a management of change review to identify how this action affected the safety of the process. The CSB found, however, that Williams did not identify that the new valves could isolate the reboilers from their protective pressure relief valve. Companies are required to conduct a management of change review before making equipment changes, so they may consider the impact of that change on the safety of the process. But the CSB discovered that Williams conducted the management of change review after the process was already operating with the new valves.
We concluded that Williams conducted.
I've cut the video short because there's not a lot else on it. So, I mean, that's three short case studies we popped up, but it's got some common themes. Ignored warnings from the shop floor of things that had gone wrong, from outside the company, knowledge of other events and incidents, poor management of change, technical risk assessment, and no human factors considerations. All of those things contributed to those disasters, and unfortunately you get them every year. I could have picked three other videos, more recent ones. They continue to operate. European Process Safety Centre surveys its member companies every year, and in 2022 we had 37 companies respond, covering 1.7 billion working hours, and 1,600 incidents. And when we did the analysis, more than 50% of those incidents were due to operations. So this is why it isn't just good enough to do the technical design and the HAZOPs and everything else, but also really do need to look at those operational tasks, because very often they're not in those HAZOPs. They're done afterwards when the project engineers are leaving the plant, maybe. Any questions about that? This is all about bypassing, I think.
Okay, so yeah, I've been monitoring the chat. There was a conversation with regard to the first incident about whether there ought to be, or indeed is, regulation of safety critical devices. I think what's something that you might reflect on for us, those that have been presenting, is around there may be times when there is no choice but to override some kind of interlock or safety critical device. Maybe it's a startup, turnaround, various types of things. What's your view on how that decision ought to be made and how it ought to be managed?
Well, in the absence of anybody else talking just yet, that's what management change is for. That's the whole point. We did a whole webinar on that, but you can do it as complex or simple. But the point is, if you get the right people in a room, or even over the phone or on Teams, and have a discussion, because no one individual can envisage the implications of making that change. Whereas you've got a group, it's like a pub quiz. You always get more answers right than if you talk on your own. So that's my perspective. Okay, thoughts from either of the other case studies? Yeah, there's some stuff about warning signs, that warning signs were missed or not acted upon in the chat. Perhaps the reality on the shop floor was not understood by managers and leaders. In terms of the second two case studies, that seems to be relevant, but I'd be interested in thoughts from those of you presenting. Tim?
Yeah, I think you just got to make it very, very hard to do things wrong. And so I think things like with the case study that I presented, having sort of dissimilar connections for emergency and more standard operational connections. So with respect to the air connection, and then also just visual indication as well. And so there was no indication as to whether or not that vessel was in a process mode or whether or not it was in a cleaning mode. And so, yeah, like I say, to make it very, very hard for an operator or an individual as a human to make those decisions to override those interlocks. And so I think that was probably what was key in that event. And then also just the idea that I think it must have been a cultural thing that when you make a mistake, you almost try and fix it by staying in the area and trying to close some valves, when realistically they just needed to evacuate the area. And then I would have thought that in that kind of incident, although it didn't touch on it, that if you were going to try and introduce some mitigation, that you should have been able to do that from a remote place in a control room that in theory had been adequately designed to withstand a blast, and you'd be doing that from a safe area. So I think that will be some of the key learnings from the presentation that I presented.
Tim, can I just jump in on that? Sorry, I try not to talk over people, but this thing about safe location, occupied buildings, it's a UK thing, and it's an American thing, but as soon as you move to other countries, you find out they're not doing it, because local regulators don't want to enforce that sort of area of surveyor. So it's a really hard one, particularly if you're in a country where that legislation doesn't make you go down that route of checking. Anyway.
Yeah, certainly with the Imperial Sugar case study as well, there were lots of minor incidents that were ignored and not followed through, and they've been around since, well, just over 90 years, and I think a lot of complacency. that the dust and the cleanliness of the area didn't really matter and wasn't an issue and wasn't a risk. They did try to go around the edges, haven't they? They'd included a dust suppression system, but not connected it to everything. And then installing the cover over the conveyor was the final straw that broke the camel's back, so to speak. And all they seemed to consider was that protecting the product and not necessarily they're enclosing a hazardous environment, and didn't connect that to the dust suppression system. But they had many, many minor incidents, and then external people came in with do you realise how hazardous sugar dust is? And none of it was listened to or sent, wasn't taken seriously.
So that's interesting, and it relates, I think, back to Richard's point about change. The enclosure of the conveyor changed the hazard nature, changed the hazard distribution, and that may not have been properly understood. Richard asks a question of everybody, and be interested if anybody has some points in the chat, is questions about proceduralizing items before you make the change. There is no reason why designers shouldn't be able to interact with operating teams to understand, well, to properly define how operations should occur. In fact, designers have a view as to how it should be operated. That, they are the designer after all. The question might then be, do they see it from the operator's perspective? So the 6-stage hazard study process that's published and promulgated by the Institution of Chemical Engineers and various equivalents around the world has phases in to look at general hazards, followed by detail hazards, followed by understanding of what happens if it doesn't go as we expect, followed by did we build what we said we were going to build, and then indeed a cyclic process thereafter. So a number of the organizations you saw in these case studies had carried out the cyclic process. So the first example, a cyclic review of hazards and operations had taken place, and it had identified the possibility of inappropriate bypassing of the valve motive power. And okay, what an organization then needs to do is act on that information, a little bit like Pamela's just said about, if dust hazard is being pointed out and you haven't recognized it, what do we do about that? So yeah, okay. There's a Tony, hello, perhaps that's the Tony I do know. Members of the operating team seconded to project design team for practicalities. Yes, absolutely. That's exactly the best way to do it. Some large projects suffer from the fact that there isn't an operating team, and organizations often can't make operating teams available. Okay, I'll let others speak. Go for it.
I also just, I mean, you don't think sugar's dangerous, but clearly it is. But I audit a lot of plants in Europe and Asia, and I can tell you today that there are companies 20 odd years after ATEX was introduced who still haven't made any changes despite the risk assessment saying they should be doing it, because they just either put off by the costs, or else when you sort of move away from chemicals and high hazard, then maybe it's a different quality or type of engineers involved, and they're introduced in maybe food hygiene and stuff like that. They're not process safety or chemical engineers. So there's a lack of expertise and competence, and that can contribute to it. But it's, as all the people are writing in, like as Lee's just put in, Lee Alford from the guy coming used to be EPSC now, Energy Institute. Let's not forget HAZOP is both a hazard and operability study. The problem is people do the HAZ bit, and it's very easy to concentrate on nodes and line diagrams and stuff like this and P&IDs, and sort of just gloss over the 1 or 2 human factors questions that you might tack on at the end, because everyone's been there 5 hours doing a session, and you don't want to be doing that. So things like SCTA and other techniques, you can pull them outside and do them with a fresh pair of eyes and in a refreshed atmosphere. So that was one of the reasons we sort of showed that technique. How we do for time? I think we probably need to. Is it okay, Richard? Unless there's lots of questions in the chat, and I'm happy to talk with people afterwards as well about this because it's sort of the day job. But maybe
well, I think I think most of the chat has been dealt with or brought up, so that's great. Thank you for those of you putting items in the chat and responding to each other, which is great. You know what, I think if we think about decision making in general, Richard's got a couple of slides that reflects back to professional engineers, and I think it would be worth thinking about engineering ethics before we move on. So over to you, Richard.
Hopefully you can see that slide.
Yep.
Right, good. There's only 2 or 3 slides. This is the problem, isn't it? This was a survey by Royal Academy of Engineering in 2022, and it actually sort of umbrella survey, including some other sources, but there were thousands of engineers involved giving responses. And this is the dilemma that many engineers have, particularly when you've got profitability, you know, you're trying to keep people's jobs going. So in some industries, you know, 36% engineers thought profitability sometimes prioritized over fitness. And some, you know, nearly half of engineers sometimes accept situations they characterize as misconduct. Half of engineers asked to take shortcuts they felt were unacceptable. And, you know, even more than half feeling uncomfortable about those decisions. And up nearly 60% finding themselves at odds with their employer when it comes to acting ethically. This isn't a long presentation, but the key thing is, could you live with yourself if you don't mention something you find that's unsafe? That's the problem. And in occupational safety, it's pretty straightforward. You can do a safety tour. You can spot the hose you're going to trip over, or the guard, you know, with a gap in it, or whatever else. They're all easy things to do. But in process safety, that's almost impossible because it's a very technical discipline. You can't tell by looking at a vessel or a pipe whether it's the right thickness, what design code it's got, whether it's got a safety valve, whether it's rated correctly, has the hazard been done. You just can't do that. So it's the general workforce. It's easy for them to be complacent because they don't have these things going wrong. It's the professional engineers involved in those teams. It's up to us. If we're not happy, we have to do something about it. Easier said than done, though. Just 3 institutes, they've got some codes of professional conduct. For the IMechE, this is our event, identify and quantify all risks and hazards associated with their work and manage them in conformity with accepted engineering environmental standards and in a manner which doesn't compromise the welfare or the health and safety of society. They shall inform those with whom they work of all matters relating to risks and hazards. So if you're a chartered or an engineer or working towards that, you've actually signed up to say you're going to comply with that. If you're from the IMechE, Richardson, both of them, members must hold paramount the health and safety of others, draw attention to hazards and prevent avoidable danger. And the Energy Institute, because that's the other one we're talking today, members will at all times take care to ensure their work and the products of their work constitute no avoidable danger of death or injury or ill health. So we all know what we're supposed to do. Actually doing it isn't so easy. So I just jotted down a few thoughts. I'm sure we could go on for pages about this. It's not an easy thing to do, and it depends upon the culture of your company. But on the sort of occupational safety side, yeah, what if you see something wrong, the guards loose, missing, there's leaks? The normal thing is you tell the local supervisor, or if that's a team leader or a manager, but always put it in writing because people very often forget things. Should we say that? Oh, so-and-so I told them about it, he did nothing about it. We'll put it in an email. It's much harder to ignore it. Don't do it, you know, in a horrible manner, but you've spotted something, you need to say it, because if that guard is missing or loose and someone goes along the following day and their arm gets chopped off, well, you know, how do you feel about that? In terms of activity, so you see contractors or your own people working at height, they're in the line of fire, they're lifting badly or just uncontrolled work. You have to stop the work now and ask the people to consider if there's a safer way. It's very hard to do. You just build it up with experience, but it's something you have to have in your armory. Even when they rectify it, still talk to a supervisor and follow up with an email, because They might just wear the PPE while you're there and then take it off again, you know, when they when you walk away. And then on the more technical level, so we've all done designs, process hazard analysis, hazards management change, FMEAs, loads of other types of risk assessments for all sorts of reasons. Well, if it's a serious concern, the facilitator needs to document it and needs to have an action to rectify it. If you don't already do this with your sort of HAZOP action lists, risk rank them, make it clear which are the real priority ones and which are the less. And even in projects, very often you do a big major project, you don't get to do all of the actions. There's some stuff for risk or budget reasons you won't do, but it should be clear which are the really important ones. And if you then afterwards, then you find it's not being documented sufficiently well or isn't rectified in a reasonable period, you talk to people, of course, but then follow up with an email, because I'm more bothered about people getting hurt, but if you're concerned about liability, then, you know, that's the email helps with that. And even print it out. If you're concerned about how good your employer is or whether they might try and sack you, you might get constructive dismissal then. And I've come across this recently, 5 yearly reviews for Seveso sites, finding that actions weren't completed from the previous 5-year review and they're still going to review them again. What's going on there? You need to escalate those sorts of things. But without risk ranking, it's very hard because there could be very minor things. Of course, whistleblowing is a possibility, but you know, your career might be cut short by that, or at least the career with your current employer might be. But if you're that worried about it, the HSE have got a web page and you can do whistleblowing in confidence. Of course, the other thing is you could just change employer, and I've talked to a lot of people, they've done it, they've left companies they don't think are very safe. As a generic thing, that's fine maybe, but if you know there's something seriously wrong and then just leave the company, well, again, are you putting other people in danger? There's a brother's keeper principle here, I think. And then final slide, and I'll put this in the chat, there's just a bunch of resources to read up more about this, and some good discussions from RAE and Professional Engineering Management, ASME, which is the American Society of Mechanical Engineers, and of course the IMechE. So I'll just stick those in the chat. I don't think there's an easy answer, and I think the more junior you are, or it's something you have to go through and get mentored on maybe, and get more confident to be able to stop anything. But the general principle I was always taught is you can't, if you know about something that's unsafe, you can't walk past it. You have to do something about it. Anyway, that's my 2 penneth. I'm sure other people have got different ways of dealing with that.
Thanks, Richard. That's a good summary. Whilst you were talking, I put some other leadership resources into the chat, which reflect a summary that we'll do much later on, but they are relevant. So there are several levels at which to consider the points Richard has been making. You know, leaders need to make it possible for people to raise concerns and to demonstrate that they will take those concerns seriously enough. And we, as professional engineers, need also to recognise that we have a duty to try and raise those concerns, notwithstanding the points Richard made. Okay. More people that I might know joining the meeting. Okay, so what I'm going to do for the next session is I'm going to invite Stephen to join us on screen, if you would, Stephen, and I will start to share my screen. We'd just like a bit of input from those of you that have taken the time to join the session this morning about what are good ways for you to access the kind of information and legacy we have from this series. So let me start my slideshow. That comes at the right page. To that is no, it does not. So, really, you know, the fact that you've chosen to join us today demonstrates that you're sort of interested in this kind of format, but Stephen and I have been pondering what might be the best way to make information from the series and the subjects covered by the Process Industries Division available to everybody. Doesn't have to be a long conversation, but ideas really in the chat, and if anyone wants to pop up and be heard, then that's fine. But Stephen, do you want to just introduce yourself while everyone's having a little think and getting their keyboard ready? Oh, you're muted there. Find the mute button.
Very typical. Team speaking. But yeah, I'll take the opportunity to introduce myself. I'm Stephen. I'm currently with the Young Members Board for the Process Division. My day-to-day is I'm a senior mechanical engineer with Halliburton, and I've been there for just over a year now. I have a mechanical engineering background, and I've been with IMechE for probably since I was an undergrad. So yeah, it's been a I wouldn't say a while, but it's been a good minute. But yeah, that's me.
Okay, so what types of media and material do people access to get their not just CPD but information? Feel free to shout or type it up. Okay, well, we may have a shorter session than we thought here, Steve. Suffice it to say, as you will be aware if you've been on from the beginning, we've recorded this session, and indeed all of the others in the series were recorded and are available online. I've got a few slides potentially to close. Okay, we've got a few things coming in, webinars, listening back, webinars. People do like the webinars. Okay. So LinkedIn being the way that people find out about it, presumably you mean, Tim, in the sense, yeah, okay.
Yeah.
Okay. Okay, and I accept that finding time in the middle of your day is not always possible for everybody. We've all got a day job largely, or at least plenty of other things going on in our life. So at least recorded prevents the opportunity to interact, I suppose. But does anyone read a book anymore? I mean, the reason I asked this because I'm an old guy. So what can I say?
I think there's a lot of these incident databases are quite good as well, but I think that they're not well utilized, I would say.
Okay.
I think they've got a lot of good information in. I think but it can be quite hard to search, and it can be quite hard to access. And I think that there's quite a few European ones in my experience, and it's not something in the UK that we've seemed to have sort of standardize and bring together, in my opinion.
Yeah, okay. I mean, part of one of the comments earlier on from Alistair, I think it was about user groups, and presumably, Alistair, you were referring to users of similar equipment or similar processes, and for sure, there are particular products around the world that particularly high hazard products like chlorine, ethylene oxide, and so on that tend to foster user groups, which is a great way to share information. Part of the problem, I think, is editorializing in a way that makes those things digestible, and perhaps that's the issue you're referring to, Tim, about how difficult they are to interact with. Yeah, okay. So several people are admitting to reading books still. Well, I'm pleased I'm not the only one. That's fantastic. Okay. Well, just
throw in. Richard. I'm sure everyone's completely aware of the monthly things, that the process safety beacons that come out from Centre of Chemical Process Safety, CCPS. Yes. And the EPSC produces the learning sheet every month, and these are excellent, completely free. And there's a third one, of course, the Energy Institute do the EI Toolbox, and that aggregates those, but also lots of other sources, people like Energy Safe Canada. And so it's like a fire hose of information, but what it does mean is you can select relevant stuff. I do it for various technical meetings, depending upon the audience. There's always something relevant on there that you can pick to them, because case studies have to be relevant, because if they're not relevant to what you do, you forget about them. You just don't think they can happen here. But if they in the same industry, in the same environment, oh, okay, you know, that's a problem. So I maybe I'll put those 3 links in the chat. I won't take any more time up about that.
Oh, no, it's okay, Richard. I mean, so those are items that people can sign up for a newsletter, essentially, and it will then come at them. That there's an interesting challenge in that you, as you say, it can be like a fire hose at times, and you have to try and sort out that which is interesting. That said, I've a challenge in a moment that says, well, isn't that part of our jobs to try and sort out the things that may not be local but might be relevant to us? Okay, I mean, I think the other areas, yes, online is, you know, we can know pretty much everything, and Wikipedia is a fine thing, but use your faculties in order to check that which is likely to be factual, or at least somewhere based in fact, and that which is not. I've done some work with Cranfield University with regard to incident investigation in our business, and they usually introduce the course by saying, we're not here to just provide material for the Discovery Channel. Although some of these incidents do make interesting documentaries, and that might well also be an area that people use. Okay, well, I think, you know, be interested to make sure that whatever the legacy of this series and other work that the Process Industries Division of IMechE uses is accessible to everybody. If there are ideas that you have later, please do connect with anybody either that you've spoken to today or within IMechE Process Industries Division, and let your views be known about the kind of nature of the information you'd like to see or be able to access in the future, and perhaps get your colleagues to do so.
Yeah, I mean, I'd just add to what Richard says. His day job is process safety. My day job is process safety. I sort of see it as a mission to share it and help people avoid accidents. Even though a lot of you are more professional and more qualified than me, if we can get together and do that in the future, we have to continue to do it, because otherwise people won't learn. And learning through training is a much safer way than learning through experience. It really is.
Okay. At which point, let me make some reflections on what we've heard today and perhaps over the series. First of which is actually learning lessons does seem to be quite difficult, despite our ability to see lessons all around us. In terms of today's information, we've talked about the idea of safety critical tasks and being able to identify those, particularly as the tasks that would lead to or potentially prevent major accidents or major incidents or serious catastrophic events. There are plenty of processes in health, safety and environmental protection for general hazard and risk management. Make sure that there is some differentiation in your organization with the stuff that could be really bad. We can see that safety critical task analysis is a robust but potentially time-consuming process, and it relies very heavily on having the right people in the room. And we related to that again with respect to design hazard study as well. The amassed brain power around the table is what makes these processes so beneficial. We've talked a little bit and referred to the idea of human factors. So humans, as your HR function will tell you, are our greatest asset. But as far as process safety is concerned, not only are they our greatest asset, but they're potentially our greatest problem. We can make humans more reliable. We can make their decision making better and more resilient to problems. So just think about how we set our people up for success, and potentially the stories we should be telling are about what went really well and what made it go well. The fact is, we should also tell stories to each other about what went wrong and what were the setting for that, because that allows us to think, oh, how will we avoid that? Noting that the safety critical task analysis guidance is free is worth thinking about. Go out there and download this stuff, read through it at your leisure. When we got into the case studies, the videos from the Chemical Safety and Hazard Investigation Board in the US, that is a free resource. There are similar resources that Richard has referred to across Europe. The Dutch Safety Board is worth looking at. They focus more broadly. It's OVV, and I will not attempt to pronounce that, so apologies for that, but if you search Dutch Safety Board, you will find that online. They also do videos. Some of these videos are only a few minutes long, as you saw. Use them in lunch and learns, use them in toolbox talks, use them to share amongst your colleagues. I saw this, what do we think about this? Could this sort of thing happen here? Even if you don't use vinyl chloride monomer, even if you don't make plastic, there will be aspects of those videos that will be relevant to you. You know, we don't mill sugar. It's nothing to do with us. Well, I will challenge that in a moment. Bear in mind that interlocks might be overridden for a number of reasons. So hard and fast rules occasionally need derogations, but derogations, as I think Richard said, should be seen as changes that need to be authorized and managed. I thought the idea of a priority alarm pop-up was a great one in Richard's example of his control room. That's duly a process that's used in aviation. You know, if there's a problem in the cockpit, the pilots are trained to reach for the checklist, and the checklists are quick, short, punchy, and allow you to do the right thing in the right order. So we can cross sectors and cross industries with our potential good processes and good practices. So finally, we were just talking about the idea of hazard study. So see the signs at the design phase. There's plenty of decades of experience of process plant to know how process plant can fail, you know, and turning the valve off below the relief valve, as we saw in the last example video, is an absolute classic. It's not as though that hasn't been done dozens of times before. So what I'm saying, therefore, is we can foresee that as a potential failure mode. Having said that, shortcuts in the field, a little more difficult to spot. We need openness to bring them up. And if operators and maintenance teams are not being seen to be being caught out, they may well be prepared to be very open about the shortcuts that happen in the field. Possibly even calling them shortcuts is bad news. You know, what are the efficiencies that you find in the field? Because humans are efficiency-seeking animals. You know, we'll always seek to do something quicker, easier next time around. And we may think, I don't need to follow the procedure in this case because I know what I'm doing. And we will think that for good reasons, but it's the sort of thing that needs to be identified in the field through, potentially through auditing, but also through cyclic study of what's happening. So, okay, that's the materials we've talked about today. I've got a couple of closing points about the challenges for learning lessons. So these are the sorts of challenges that I recognize in learning lessons. Have we got time? It's a photograph of Douglas Adams, by the way, who wrote The Hitchhiker's Guide to the Galaxy, among other things. But in The Hitchhiker's Guide to the Galaxy, there's the idea of a somebody else's problem, right? And if somebody else has got the problem, then I don't have to worry about it. Those of you that do read books may well have read that one. There you go. But if it's somebody else's problem to learn those lessons, I can get on with my day job. Sometimes it seems difficult. Sometimes it seems expensive. And you know, the example we gave around or the three videos we saw, there may well have been some updating that seemed very expensive. Going back to Trevor Kletz, who's one of his other famous quotes is that organizations have no memory, only people have memory. We have this idea of corporate memory loss. And of course, if the folk who saw it, and indeed one of the contributors was rereading a book by Trevor where the example was an incident they had first-hand knowledge of. Once you move on, your first-hand knowledge goes with you. So there is a challenge to somehow codify corporate memory. So I might have a challenge with Trevor that say, well, okay, I agree with that, but the point is we should, as professional engineers, codify what we know so that it can be passed on to people after we've moved on or decided to do something else. Another feature of catastrophic incidents is low probability. And I mentioned earlier, there is a tendency for leaders to focus on the stuff that's, look, it happened again, somebody's tripped over and broken their arm. Yep, it can happen. And it can happen at high frequency, but ultimately that might be as bad as it's going to get. The low probability events can be dismissed as low probability, but if they are organization ending events, then we need to provide the right amount of interest. The other feature, of course, is wide scale change, which might be linked to too difficult and expensive. Is to make a change in one location, perhaps I now need to make that same change everywhere. Well, perhaps you do. There may not be a good justification for having different standards in different locations, but there might. There may be different consequences. There may be other aspects that are different. So don't assume that because a change is required or reasonably practicable in one location, it will necessarily be so in others. But that is a challenge you have to take. So I would say make fewer changes and make them well is a good piece of advice that I often give to leaders. So if I think about a professional engineering approach, we can know everything. You can look it up on the internet, and then the challenge is sorting the wheat from the chaff, but you can kind of know everything. You don't have to remember stuff, perhaps like we used to, but on a personal level, be curious, read around your subject, look at other sectors, look for the general message in the specific incident, and that applies in your own sector and your own location, because it may well be that an incident with a heat exchanger is not really about heat exchangers. It might well be about operational control, and that might also apply to fired heaters, boilers, refrigeration plant, and so on and so on. Equally, materials handling equipment. Do find an opportunity to pass on your knowledge, and if where you work there aren't obvious places to pass on knowledge and tell stories, then suggest it. In fact, why not take the initiative, set one up? Everyone can bring their sandwiches, and over lunchtime a lot can be discussed and a lot of knowledge can pass back and forth. And it's particularly the case once you get some experience under your belt. Take the opportunity to pass on knowledge. And when we talk about leaders and managers, if you manage and lead in an organization, make sure that passage of knowledge is valued by what you do and what you say. You can check it's happening. You could measure it's happening. If there's a lunch and learn process, you could measure who turns up. It's a leading indicator to the transition of knowledge. And you should take part. It's okay to delegate, but if people in an organization see senior folk taking part, then it seems to be important enough for them to take part, so maybe I should find it important. Okay, and then we talk about organizational learning. Codifying the lesson is important. How should this thing be done in the future? Communicate the way of working, and I talked about this much earlier. Check it's happening. If we want to make a change, we need to build the new process into our discovery processes, into our auditing. We need to check that the new way of working is what is happening. And I would also say that for assurance audit, make sure it's an opportunity used to educate and not just to check. Your assurance auditors may well be people with broad experience, and that's why you've chosen for that task. they can spend time saying, well, here's what I saw elsewhere. Have you talked to so and so on another site, another part of the business? They've done some good stuff here that you might want to steal with pride. So have managers understood the data, and particularly where you make change, measure whether the change has happened, measure whether it is in fact having the effect you wanted it to have. I would close with the question we asked right at the top, and the title of today's webinar is Process Safety Management for You. Because we're talking about the prevention and avoidance of high consequence incidents, those may or may not obviously be around, but they are around in a lot of industrial activity, the potential for them. So maybe shouldn't be seen as a field solely associated with the process industries. We've some demonstration in terms of the examples today. We've got this idea of combining specialism, forward thinking, brain power on what has to go right. And even if that's mundane, getting people to think about what must go right is important. However, we do need competent people and routine sharing of lessons. But I would just want to point out that elimination of hazard is by far and away the most significant way to reduce process risk or catastrophic incident risk. So watch out for a race to the bottom of the hierarchy of risk reduction that's shown in the image here. So I do think process safety can probably be applied in very many locations, and indeed beyond engineering activity as well. That focus on what's got to go right and is a useful set of questions for any business leader in any setting, I would say. So we think the answer is yes. I hope those of you that have joined us and are still here agree that the answer is yes, and we will endeavour to keep this kind of information current through what the work of the institution. So these are the resources that I put into the chat earlier, and particularly around leadership. If you've never seen the OECD checklist, it's simple and easy. The Institute of Directors and Health and Safety Executive checklist, INDG 417, free to download. Useful challenge if you're a leader, useful challenge to your leaders if you're an advisor to the leadership group. Then we have various organizations involved in upskilling sectors of the population and engineers in general. So we look forward to hearing from you. If you would like a CPD certificate, get in touch with Murat. His email is there. I will come back to this slide in just a moment. I want to say that there are webinar recordings. So go in through the Institution of Mechanical Engineers website and you'll be able to get to the Process Industries webinars. There's the YouTube channel, youtube.com, IMechE UK. So I'm going to leave this final slide. Please do give us your feedback. Let us know what you thought, and happy to be connected through LinkedIn with anybody who found the information interesting today. And hope you have a good afternoon, or whatever part of the day it is for you, wherever you are in the world. And we'll see you again. Thank you very much.
Oh.